Wait for a few more minutes, Madhukar.
Yeah, yes, sir. I think, yeah, we'll wait
Yeah,
for.
you should wait for some time. Siddharth is going to join us.
He may not.
Okay. Okay, I think you should start at 3:35. That's the.
Yeah, okay, sir. I'll start at 3:35.
Yeah, I think you should start. So Sahil is usually there, but maybe he will join a little bit later.
Yeah, sure, sir. I'll start. So are the slides visible?
They are.
Okay. Yeah. Hi, everyone. So we'll take it up from where we had left. We had left last week, and so we had looked at neural network from the verification angle. So we realized that we have to study these artifacts, which are nothing but those created out of a machine learning algo, which is you train something into you're trying to solve a problem, you train that thing into a neural network. For instance, we looked at the example of this airborne collision avoidance system, and we tried to replace. I mean, we saw that the motivation was to replace this 2 GB of lookup table into a less than 3 MB sized neural network. But if you are able to, if you're going to do that really in a software which is going to be used for any critical system, you want to verify certain properties. So this is what we are looking at, and we will understand these things a bit more in today's lecture. So this is a quick recap of what we had done. This is just one example that I've borrowed. I'll not go over this example again, but somebody had remarked that they have not looked at Z3. So I've added a link to a tutorial on Z3, which is an easy to do thing. You can take a look at it. Of course, in the next class we'll try to do a much better and a more a slightly more organized way of looking at some of these Z3 examples and how we can use Z3 to encode certain problems and find answers. But in the meantime, if you would have looked at the script, the code, that the Z3 code for this particular program that you see on the right, it's not very difficult. The Z3 really, I mean, you define some three real variables, and Z3 really simply encodes the mathematical constraints. So you can, even if you don't know Z3, if you had taken a look at these examples, you'd know that this exactly encodes the program. In any case, here is I've added a link to the Z3 tutorial, and you can take a look at it. Hopefully things will be clear. If anything is not clear, you can certainly send an email to me or any of us for that matter. Okay, so what were we doing? We're looking at this network. It has this one in particular had an input layer and an output layer with one neuron each, and a hidden layer with two neurons, and there were some weights. There were no biases here. And we know from what Hitat told us that biases are not really, they don't add to the expressive power. What you can do with biases, you can do without biases. So this is not less expressive in any way. And on this network, we wanted to specify and verify certain properties, namely whether the input always matches whether the output always matches the input, and some other properties also, that can you find an input in some range such that the output is in some other range. This is what we had looked at. Okay. And yeah, so going ahead, so we'll try to see how do we look at them as graphs, which is nothing different from what we have been looking at anyway. But this is just a way to systematically put things down so that we can argue about them later. Okay, so there is no rigorous definition of what deep learning exactly is, and so what we want to do, and we have been seeing it, that we can define neural networks generically as graphs of operations over reals, and we know we have been seeing these things. The graph, of course, has an architecture or a shape, and the shape is not, it's not just arbitrary. This is the shapes suit a given task. Okay, so you build networks which are suitable for a task, and the shape of that may depend on the task that you're doing. For instance, if you're building a network for image recognition problem, then that may look different from one that if you build for natural language processing. Okay, so the point that I'm trying to make here is that there is some underlying architecture, and it's not just arbitrary. It has some meaning to it. Okay, so before we go ahead, here is a quick recap of some of the things that Hitarth had done, but to look at it in a very simple way. So here is a very small network. So you have X as the input neuron, V is a node, and Y is the output. And here you want to compute what this network is. You want to compute the function which is being computed by this network. So what is so suppose if we know about activation functions, right? So we have looked at this activation function called ReLU, which looks like you can see the graph at the bottom. It looks like this. So for X is less than equal to 0, it is the function gives you 0. Otherwise, it gives you X. Okay. So this is the graph, and if you suppose V computes this transformation which takes the input X and transforms it into 2 times X plus 1. then what this network is effectively computing, if you want to put relu as the activation function, then the network is effectively computing max of 0, 2x plus 1. Of course, you can change the activation function, you can change the transformation, you can change whatever. So for instance, if we keep the same transformation that x goes to 2x plus 1, but change the activation function to sigma, which is sigmoid shown below once again. So you can see that f of x is sigma of 2x plus 1, where sigma is 1 plus 1 by 1 plus e to the power minus x. Okay. So one can do all this. You can transform, and these are the only constructors that you have. Okay, so you have your transformation, you have your activation function. Okay, but the point is that with just this, what is it that you can do? What is so special about these activation functions? And the answer is that they work in practice. Okay, so these are useful things. No matter how complicated or simple you feel they are certainly very useful things. And while they are useful, they help neural networks learn complex tasks. Okay, and with respect to that, there is something called universal approximation theorem. So what this essentially says intuitively is that you can construct a network comprised of these relus or sigmoids, and such affine transformations, where you are multiplying integers by constants and adding constants to them. You can do this to approximate any function, no matter what function you want to approximate, you can do this to approximate that function. Okay. And in fact, it is even more surprising than that. It says that you can do it just with a single layer. So you have your input layer, you have your output layer, and you have one single layer between them. Okay. So this theorem says that feed forward network with a single layer is sufficient to represent any function. Of course, but the layer may be infeasibly large and may fail to learn or generalize correctly. So those are problems. So we are not saying that look, you can efficiently learn anything and everything and be done. So forget the size part of it, or whether you will be able to learn your weights and biases correctly, whether you will be able to generalize correctly, whether or you may just end up remembering whatever your input or training data was. So how well or not you may be able to learn is or generalize is one thing, but the point is that a network with even a single layer of hidden neurons is sufficient to represent any function. And of course, there is a lot of discussion on this, and discussion in the sense that people want to intuitively understand why this is true and why not. And here is an interesting essay that you can read on this one. This is from a book by Nielsen. Although it's the chapter 4 of this thing, but it doesn't require you to read the first 3 chapters. This is an independent thing in itself, so you can take a look at it. Okay, but the point is that this is why we are interested in looking at them, because no matter what your function f might be, we can learn it. We can learn a good approximation of it. Is the point? Okay. So of course we have seen graphs like this earlier. So they are layered graphs. So you have 2 hidden layers in there. The x1, x2, x3 are your input layers. y1, y2, y3 are your output neurons. And you can think of them as doing some classification. So this is a multi-layer perceptron or whatever. So you can think of this as you're taking this x1, x2, x3 as input, y1, y2, y3 are the output. And you can also think of them as doing some classification where y1 is something belonging to the class y1, y2 is something belonging to the class y2, and so on. Okay, so the output neurons may represent some classes, and when doing classification, you can think of that as the weights that you get at y1, y2, y3, representing which class your input belongs to. Okay. Yeah, or in other words, the value of those neurons represent the probability of that class. Of course, for it to become probability, you can't just have it as y1, y2, y3, because they may be arbitrary, and it's not clear that y1 plus y2 plus y3 is 1. Okay. So what is typically done in such cases, especially if you're doing classification problem, a softmax function is applied to normalize these probabilities. What is the softmax function? This is e to the power xi by summation of all e to the power xi. So this one, for instance, is yi e to the power y1 by e to the power y1 plus e to the power y2 plus e to the power y3. Similarly, for the probability of y2 is e to the power y2 divided by e to the power y1 plus e to the power y2 plus e to the power y3. Okay. So once again, we can get into why this works, but that's not the point. The point is that you can see that it works. So if the probability is sum to one. Okay. So that is something that can be seen, and of course, you can notice that this is non-linear, and it's difficult for in general. It's difficult. It's more difficult to reason about. Okay, so what is an alternative? An alternative could be to add a custom layer to do this normalization. For instance, you could have simply done y1 by y1 plus y2 plus y3. Okay, and so you could have simply added a layer which would take from all these things. From it gets an edge from y1, y2, y3, and at the top thing it computes y1 by y1 plus y2 plus y3, and then it computes y2 by y1 plus y2 plus y3. And then at the third neuron, it computes y3 by y1 plus y2 plus y3. Once again, it adds up to 1. Okay, so you can do these to do your to do classification like this. Okay, so one of the examples that at this stage we thought it would be interesting to present and discuss an example. So here is what we had in mind. Okay, so suppose you want to train a neural network to detect primes. Of course, primality testing is a difficult exercise, and perhaps neural networks are not the most suitable way of doing that. Especially if you have an algo of doing that, why train a network? You can simply write down the code for the algorithm. Correct. But let's say we want to do it, we still want to do it. It's not about training a network to do it well or not well, but it's about training a network and then asking how well has it learned, if at all. Okay, so we can do it in many ways. So one of the ways is that so let's say that we are restricting ourselves to 8-bit integers. Okay, so we have these 8 bits, which is okay. So in 8-bit integers you can go from 0 to 255. Okay, and suppose I restrict the network to have only 2 hidden layers, and even in those hidden layers I restrict it to have only some 4 neurons in each layer. Okay, so this is how my network looks like. I have 8 neurons in the input layer. Okay, and then I have 2 hidden layers with 4 neurons each, and then I have a y1 and y2 like I had in the last slide for classifying whether they are prime or composite. Okay, so you can of course here is a task, here is a network, so you can certainly train that network for the task. How do you do that? So you can train by actually giving it primes. So there are 54 primes which are less than 255. So you can take those 54 primes and some of those 54 primes, and you can take some composites, and you can use this to train this network. So what is this network being trained for? This network is being trained to detect 8-bit numbers as prime or composite. Okay, this is what we are trying to do. Okay, so we have taken this training data, we have taken some primes, some composites, and we are trying to train this network. Okay, and like I was telling in the last slide, instead of softmax, you may use x by x plus y and y by x plus y in the output layer. Okay, so we can do that, and we'll see why we are interested in doing like that, why we want to construct this example, so that we can ask some properties about this, even though we may not ask entirely whether the network will be able to detect all primes precisely. Maybe there is something that we can ask about this network. So here is what we had in mind. Unfortunately, we have not been able to construct this yet, but yeah, but we are trying to do that, and hopefully in the next class I'll show you how this can be done. Okay, Okay, so moving on, yeah, Hitat also told about these convolutional layers, which is, for instance, he gave this example of this image, which is, you have these pixels, and so you can take a region of your input and then, apply some kernel on it and get some output, and then that output is what is, so you add a layer to get that. Okay, not only for computer vision in general. So the idea of this convolutional layer is more general. So basically, you want to apply some kernel to some region of the input. However, you define the kernel and however you define the region. Okay. For instance, suppose you're doing an NLP task and you have a 4-word sentence as input, and x1, x2, x3, x4 are your 4 words. Okay. So you can define a kernel which applies to every 2 consecutive words. So okay, so you can define a kernel which acts on x1 and x2, and then and then x2 and x3, x3 and x4. Okay, so you can define a kernel, an operation that is applied on some region. So you can define your region and you can define your kernel. So it's not just restricted to. I mean, of course, it's used quite often in computer vision, but it's not. It does not restrict you from using it just there. You can do this elsewhere also. Okay, and typically this is done to reduce the dimensionality, because you don't want to, you want to somehow summarize. So Hitat, if you remember, Hitat gave this example where you're looking at a 2 by 2 matrix, and instead of trying to capture the entire matrix, you're approximating it by saying that I will take the maximum of the 4 entries, and that will become an entry here. Okay, so you want to essentially capture what is happening approximately, so that the task becomes easier or better. Yeah, so this is something that we have seen. Now, what about loops? Of course, can neural network have loops? So they can have. No, so although in practice it is not true. In practice, what we see are mostly directed acyclic graphs, because this makes training using back propagation possible. Okay, but you can see it's not that they're not there. You can see them in recurrent neural networks, for example. But even when they're there, they're not really problematic. They're harmless. And why are they harmless? Because you can find out the number of iterations statically. Okay, so you don't need to run the network. You can, for an input, you can find out the number of iterations statically, and then you can simply unroll the graph. Okay, so so basically, the graph becomes as many times bigger, but you escape the question of loops. Okay, so in principle, we'll not have to worry about loops. Notice that if you're trying to verify programs, this is not how it works. The number of iterations is almost always not cannot be determined. I mean, quite frequently, it cannot be determined statically, and therefore this is very complex. When the loops are a problem when you have to verify programs. Here they are not so much of a problem. They are harmless. Okay, so they are in recurrent neural networks. So and it's important to mention this, because when we have this view of neural networks as DAGs, you should understand that it is, they can have loops, but you can unroll them. Okay, another important thing before we move to specifying properties about neural networks is the property of these operations. Okay, the operations that we are doing. What are the operations that we are doing? We are doing this transformation and activation. Okay, so the operation needs to be differentiable. So here we are talking about why we use relus or any other function, and what is the property that we expect. So the property that is expected is that the operation needs to be differentiable, or at least differentiable almost everywhere. For instance, this relu thing is differentiable almost everywhere except at x is equal to 0, where there's a sharp bend. Okay, and to get this thing in place, we are we look at linear or piecewise linear functions. So linear functions are things that look like this on the left. So you have this cixi plus b, where ci's and b's are some real numbers. Okay, So this is linear. And on the right, you have piecewise linear, because in different for different x's belonging to different disjoint regions, it is linear. The whole thing is not linear, but at least piecewise it is linear. Okay. So for instance, ReLU can be represented like this. So you write ReLU of x as 0 when x is less than equal to 0, otherwise it is equal to x. Okay. So the ReLU is piecewise linear. Okay. Monotonicity is another important property, and it will help us in our analysis, and we'll see why. And both ReLU and sigmoid, as you have seen, I think here, you can see that they are both monotone. Okay. Okay, so now we know. I mean, of course, most of this we had, some of it at least we had looked at earlier. But
Yeah, Madhukar, just to make sure that everyone knows what monotone is, what a monotonic function is.
Okay, yeah.
So just remind them. Yeah, so for bigger and bigger arguments, they give bigger and bigger result.
Correct.
That's what monotonic is.
Correct. Or if you, yeah.
If x is greater than or equal to y, f of x, then fx will be greater than.
Correct.
Fx will be greater than or equal to f of y. That's what.
Correct. Which you can see here that the graph never dips. It never, the value at a previous point is never more than the value. As you move along the positive x, it's either greater or equal. It's not less. It doesn't become lesser at any point in time, which is what is monotone here. Okay. Yeah, sorry. Yeah, so now we'll try to specify, and we'll understand what it means to talk about properties of neural networks, because this is what we want to do. We have been, I mean, we have looked at, that we can construct neural networks, we can train them, which is fine, but we also want to argue about them, and we will look at, how do we specify properties about them, and then with some knowledge of constraint solving and SMT, we'll also learn how to verify these properties about the networks. Okay. So first of all, what's important to note is that the properties that we are interested in are the ones that dictate the input-output behavior. It's not about how the network internally works. It's only about the input-output behavior. Okay. It's not about we are not going to talk about how the network is computing whatever it is computing and so on. We'll worry about the input-output behavior. Okay. And in today's lecture, right now we are interested in specifying the properties. We are not interested in verifying them. So we'll look at only specifying the properties. What does it make sense to specify these properties formally and so on. So restriction, yeah. So one of the things that's important is that so when we are specifying, today we'll specify all kinds of properties. When we are verifying them, remember that uh, when we are verifying, depending on the verification algo that you're using, you may have to restrict your properties. You may not be able to verify all kinds of properties. That depends on the power of your verification technique. Okay, so you may not be able to verify all, so you may have to put some certain restrictions. For instance, I mean, it's true everywhere, right? It's true even for programs, and in general, the more expressive the language to specify the property is, the more difficult it is to verify. So so between specification and verification, we have to remember that we will need to restrict some amount when it comes to applying verification algorithms. But the point is that right now we are not going to worry about it. Okay. So how will our specifications look like? Our specifications will look like pre-conditions and post-conditions. Okay. And the meaning of that will be that if the input satisfies the pre, the output must always satisfy the post. Or if you're asking this as a question, then we want to ask the question that if the input satisfies pre, will the output always satisfy post? Okay, for instance, if you want to if we go back at this primality testing example, we we may be interested in finding, so what would be a correctness thing of this? The correctness thing would be that it should be able to tell me exactly if a number is prime or not. If it will be the network should be able to tell me exactly whether an 8-bit integer is prime or not, which we are not specifying right now, because we are not. But what if we want to specify a weaker property? We want to specify this property that if the number is even and larger than 2, then the network should have certainly learned that it cannot be a prime. Okay, so the network may not have been able to learn what are primes, what are not, but we expect the network to at least learn this much, that anything even and bigger than 2 is certainly not a prime. Okay, so we can specify such such properties. Okay, if the input is an even number bigger than 2, so this being the precondition that it is an even number bigger than 2, then the network will always output composite. Okay, which is the post condition. So we are always going to specify our property as pre and post, and here is a pre, here is a post.
Yeah. So since you're making a point about what kind of properties and so on, of course, there could be several kinds of properties of interest that we want to verify. You've given a whole bunch of classes, but the point of this course, okay, since we'll be talking about SMT solvers and SMT logic, the idea is to see how SMT logic can be used to model, as well as how we could, given a particular verification problem, a property that you want to verify, how to reduce that through, how to eventually reduce that to using, reduce that to an SMT verification problem. Okay.
Correct. Yeah.
And that's what we will look at. Of course, SMTs, bare-bone SMT, when you use only quantifier-free logic, it may look very pretty limited. Okay, but imagine that you could make multiple calls to an SMT solver, and you can build a layer. So that could be a program where you will be making calls to SMT solvers, multiple calls to SMT solver. Then you may be able to verify something which is more sophisticated, more expressive than just quantifier-free SMT logic. So maybe you could explore that in in your project. Okay, and also rather than modeling the whole thing in a monolithic way and then shipping it to SMT may not work. Okay, because of the scale of the problem, number of nodes and the kind of functions and then nonlinearity. Then you may want to split or decompose the verification problem into smaller pieces, more in a um, in a more calculated way, so that individually the problems can be converted into SMT logic, and then you can put the entire verification, compose the various verification problem to one. Yeah, those are the things that you can use to extend the power of SMT. So I'm making 2 points. So because of the subject matter of the course, we will be looking at reduction of this verification problems of various properties that, some of which Madhukar will be showing, into SMT logic and decomposing them to address the scale as well as extend the class of properties that you can verify.
Yeah.
Go ahead.
Yeah, certainly. So one of the things when we were talking about properties last time, we had looked at safety properties, security properties, and consistency properties, consistency with respect to certain laws that we know. or whatever. We had remarked that robustness properties are the one which are the most talked about. So we have a few examples of robustness properties here, and they they're also there in slightly more detailed fashion a little later. Okay, so for instance, so suppose you have an image, and if a network predicts a given image C as let's say a cat, then one example of robustness property is that if you take any image which is like C, except that it is slightly brighter or darker than C, must also be predicted as a cat, right? Because this is a desirable property. So once again, you may not be able to specify the correctness of this network which is predicting images as cats or not cats, because you cannot mathematically specify what exactly it means to be a cat. But even if you can't do that, you still have a desirable property that you would want to prove, and the desirable property being that you take an image, you decrease its brightness or increase its brightness maybe just a little bit, then if the original one was being predicted as a cat, the new one should also be predicted as a cat. Okay, so this is one thing. There are examples of robustness properties in natural languages. So for instance, if you take an English sentence C, which is so let's say it is classified to have a positive sentiment. Now, if you take one such sentence which is being classified to have a positive sentiment, but if you add a few typos, I mean, of course, these things are not very clear now. Yeah, I'm not stating them very formally. What do you mean by a few typos? How many typos? What do you mean by a typo? How many how many characters are not in their right place, or how many characters are how many characters far from their the desired character? These things are not very formally defined, but let's keep it vague for now. So what we are saying is that if you take an English sentence, if you add a few spelling mistakes, then should it have the same sentiment? Or for instance, if you take an English sentence and if you change a word by its synonym, will it continue to have the same sentiment? And then you can also combine these two questions. You make a few spelling mistakes and also change a few words into their synonyms. Will it continue to have the same sentiment? So you can ask such questions, and this is what we are interested in doing. How to ask these questions and then how to answer them. Okay. For a code, so suppose a piece of code is detected as malware. So now so you know that this is being detected as malware by a neural network. And what happens to something which is equivalent to that code and also syntactically similar? It may not exactly be the same, but it is syntactically similar and it's behaviorally equivalent. Once again, it has to be clear what syntactic similarity means. It has to be stated mathematically, logically, formally, right? But here we are just stating what we mean by robustness properties. We mean by properties of this kind. We mean that we want to verify properties of this kind. And of course, robustness is not the only property. We looked at safety properties. For instance, if you recollect the airborne collision avoidance system, we had talked about this property that if an intruder aircraft is approaching from the left, then the controller of your own aircraft should never advise you to turn left, which is a simple safety property. Think about it.
I have a question here.
Yeah, sorry. Yeah, tell me.
Yeah, so would we be interested in two programs that are syntactically similar but not equivalent? Should they be detected? That doesn't make sense to me.
No.
Is it possible for a program to be not equivalent but syntactically similar and still be detected as malware?
Correct. No. So whether this is possible or not, we are not getting into the possibility of this. Remember that the question that we are asking is of verification, right? So we want to know if the network is capable of doing this or not. If it is not capable of doing this, it will produce a program which looks syntactically similar, but it is not being detected as malware, right? So suppose the case of primality testing. So you may say that, look, I don't believe that there is a network that you can train in one layer or two layers with 4 or 5 neurons. that will actually detect prime numbers of 8 bits, right? So you can say that, look, I don't think that's possible. It may indeed not be possible, but we are asking the question of verification. So we are not worried about whether that is possible or not. The only question that we are saying is that, look, if it is possible, we should be able to prove it. If it is not possible, we should be able to get a counterexample. Does that make sense?
Yeah. So I'm just confused by this conjunction, because if you state the program should be equivalent, we should be done, right? It's not clear to me why you need to add and syntactically similar.
Okay.
Yeah, I think Madhuka's example, Sahil, you should not take it literally. So what would you think? Okay, well, of course, he has not defined what exactly being a code being malware is. Okay, malware means it has to be doing something mischievous, correct? So what I guess the point that you're making is, if they're syntactically, if they're equivalent, the program are logically equivalent or functionally equivalent, then if one is a malware, then the other need not be a malware. Is that the point that you?
No. I'm saying if we know that it's equivalent, there's no other checks to be made. We're done.
Hello, how do you know that? No, that I don't believe that. I don't believe that because maybe there is usually malwares, they may be functionally equivalent, but in terms of the basic instructions that it is using, may be susceptible to doing certain things. Okay, for example, if you use certain features in the certain primitives in your code, then you may be able to inject some attack or something like that, okay? Which by exploiting some thing in the hardware on which it is running, misusing that, that there is some kind of a bug or some unintended thing in the hardware that you may be able to exploit if indeed you're using certain features. Okay, so these kinds of things are possible. So even if they are functionally equivalent, because you're doing some things differently by using different set of primitives, you may be able to exploit certain insecurity, lack of security in the underlying platform. Okay, so that may be what may define what malware and a malware is. Okay? In which case, your two programs could be functionally equivalent, but one could be free of malware, the other one could be. I mean, it depends on how you define malware. Okay, now, whether that is a standard definition of malware or not, I don't know.
So yeah. Are you saying that this kind of thing might be captured by syntactically similar for a suitable definition of syntactic?
Correct. Yes.
Okay.
Maybe up to certain. Yeah. I mean, I can imagine. So yeah, it could be. So, but I
guess I'm just surprised that you might be able to infer something from the syntax, but not from program equivalence. It's just maybe a little surprising to me.
Correct. No, so it's okay.
Security is certainly one feature, where you can write an equivalent program, but still one is susceptible to, one is more secure than the other in terms of information flow.
Correct.
Yeah. Certainly, some equivalent programs, one of which is more secure than the other. The other one has loophole for security. If the property is information, high value information flowing to a low value information, content. I can construct examples of that kind. Now, whether that is a suitable thing for checking as in terms of neural network, I don't know. Okay, that may be
right. Yeah. So maybe the example you mentioned, if later on, maybe I'll just ask you about it. That'll probably clear it up for me.
Okay.
Correct. Yeah, I can give you a brief example if should I, sir?
I mean, if you have the security example, you could, or you could. I mean, if you want to finish up what you have and then come back to it.
Correct. Yeah.
Later.
Yeah.
Okay.
So maybe I'll finish up whatever I have, and then I'll come back to this example. So I'll tell you how there are these two programs which are
Yeah, but
practically
for
similar and doing
security,
the same
certainly
thing.
you can. Okay. I
Correct.
think you have examples also.
Yeah, I do have an example where yeah, I'll come back to this. Yeah, but we do agree that no matter how, but remember that now we are already asking questions which are domain specific, right? So we are actually asking questions, and we are making. So for instance, this remark that we made just now, that if it's equivalent, it better be detected as malware. Certainly, there are no other questions to be asked. But how do we know that? Maybe it's true about this domain, that if it is equivalent semantically, then there's no question of one being malware and the other not being a one, right? But remember that we are already asking questions about we are already making statements which we know only by domain knowledge. So the point that I'm trying to make is that the specifying things are difficult, in general a difficult task. But the thing is that once you have formally specified whatever is to be specified, can we check it is the aim of our exploration here.
Yeah, but
Okay.
I mean, I wouldn't mind making in your project. Okay, here I have a question about a comment to make about project. Although next week that will be the subject of a lecture. Okay, of a lecture. So when you look and see, he's giving and Madhukar has given a different kind of applications. You should be thinking about those applications as well. When you make. I mean, we are more than welcome to, for you to make, give inputs into defining your project. We'll give an overall skeleton, overall framework for doing it. And if you want to add your inputs in defining the scope or the actual nature of the project, then you can, so you're welcome to do that. And these questions that you raise may be something that can be incorporated and discussed based on the project. Yeah. And we are defining the project. Yeah. So from that perspective, I just wanted to slightly disagree with what Madhukar said. Okay, although the subject matter certainly is how you verify, but the specifying for a particular application is also equally interesting. And some of that can be part of your project definition work as well. Okay, and that's the only point of slight clarification that I wanted to make.
Correct. No, yeah. So certainly it makes a lot of sense. Yeah. So when I said that, yeah, we are interested in verifying, we meant that we have been able to specify it exactly and cleanly. Of course, we can worry about how to specify it exactly and in what domain, what specifications for what problems are meaningful. That is there. So these are two different things. What could be what could be a specification for some example or some application in some domain, and then how do you verify that is. Yeah, so both are certainly important. Yeah, what I meant is that I'm assuming that a specification is given.
Yeah. So that's actually the reason. See, usually in the past, when I offered this course, I would right away get into discussing about the internals of SMT solvers and the various algorithms that go into it. For the first time, I'm doing it slightly differently with Madhukar, that's help, where we are spending significant amount of time in the beginning of the course discussing about the domain, and in this case, neural network, and also these various points, so that you will start thinking about defining your project right in the beginning. Okay, and hopefully by the month end, we should each of you should have with your partner what it is that you want to work with, so that as I will start talking. We'll start discussing more about the SMT algorithms. Okay, so these things we want to do it in parallel. I mean, that is the objective.
Yeah. Yeah, certainly. Yeah. So specification is certainly an interesting exercise, and we can of course, please feel free to to explore. How would you specify certain task for certain application, and of course, we'll verify it definitely. Okay. So this is So this is some examples that we had, and we would like to make things a little more formal now. Okay. So let's say we take this brightness example, and let's assume that the image is a grayscale image, which by which I mean that every element of that image is nothing but the intensity of a pixel between 0 and 1. Okay. If it's towards 1, it is bright, and if it is towards 1, it is dark, and if it is towards 0, it is bright. Okay. So let's say that we are trying to define what this grayscale image looks like, and now we want to define what it means to make it a little brighter or a little darker. So by that we mean that if you take element wise comparison, then every pixel should so x is our new input here. So you take any pixel of x, it should differ, the value of the intensity, the value of its intensity should differ from the corresponding pixel in C, by not more than 0.1. Okay, so this is mathematically restricting the difference between the brightness. Okay, and now you give x to the network, it gives R1 as the result. You give C, which was your original image, to the network, you get R2 as the result. And the property is that the class in which R1 belongs should be the class in which R2 belongs. Okay, this is what they should be classified in the same way. So this, if you read it from top to bottom, it means that if the brightness does not differ by more than 10%, then they will not be classified differently. Okay. So if if you are aware of Hoare logic, or even if you're not aware of it, we'll talk about it in more details later. But the way of writing this is this pre-post style of writing, where x the absolute value of x minus c less than equal to 0.1 being the precondition, the classes being equal being the post condition, and this is what the R1 is a f of x and R2 is f of c is what the network is actually computing. Okay. So starting from this precondition and the network computing what it is computing, you want to establish that the post condition holds. Okay, and this is this way of writing it is called specifying as Hoare logic or Hoare triples. Okay, so what are the three things here? There's it's a triple, right? So what are the three things? The three things are the post condition, the precondition, the post condition, and the computation, which is the network part of the thing here, which is right in the middle. Okay, and notice that this is implicitly universally quantified over x. Okay, so for all such input where the difference is not more than 10%, you want them to belong to the same class. Okay, so this is implicitly universally quantified over x. Okay, so now what do we mean by this this Hoare triple? What do we mean by the correctness with respect to this Hoare triple? We mean this statement which I have written here. We mean to say that for all x, remember that I just told that this is implicitly universally quantified. So for all x, if the absolute value of x minus c is less than 0.1 and R1 is equal to f of f of x and R2 is equal to f of c, this implies that class of R1 is equal to class of R2 is valid. Okay, so we want to check the validity of this Hoare triple. Okay, so this is the excuse me. So this is the question that we want to, this is the thing that we want to check, that whether this is valid. This is a valid formula. We know that a formula is valid if and only if not of that formula is not satisfiable. Okay, so in the second line I've simply negated the formula and I'm saying that this is unsat. Okay. So how have I negated it? So the for all becomes there exists, and you have the antecedent and you have the negation of the consequent. Okay, so here I have class R1 is not equal to class R2. Okay, so if you read it, what does it read as? It reads that, does there exist an X such that the X does not differ from C by more than 10%? And R1 is the value of that the network F gives over X. R2 is the value that the network F gives over C. But R1 and R2 get classified differently. And you want to ask this question that does there exist such an X? Okay. So what have we done? We have reduced the validity problem into a satisfiability check, okay, by negating the property if you really think about it, okay. So this is what we have done. We had this Ho triple. We wanted to check whether the Ho triple was valid. We changed this into we know that something is valid if and only if the negation is not satisfiable. If somebody has a question, they should stop me and okay. And since I can't see chats, it's better to unmute your mic and say that I have a problem or I don't understand something. Okay. Yeah. So what I was saying that we are checking the validity of this Ho triple. The validity of this Ho triple is the validity of any formula is same as checking the unsatisfiability of its negation. So we negated the thing and we want to check whether this is unsat, which essentially reduces to a sat query. Okay, so now we give this and we want to check whether this is satisfiable, and therefore an SMT solver like Z3 comes into the picture. Okay, so this is the question that we give to Z3 to find out this X. If this is indeed satisfiable, Z3 will come back and tell us the X, which is what was happening there. If you remember in the last class, we had this demo with the TOI example. Okay, we negated the property. We wanted to know if Z3 can give us an input, and we saw that wherever it was satisfiable, Z3 could give us that input actually. Okay, so this is how it is done. Okay, more on this later. How is this formula exactly solved? More on this later when we go into the details of SMT solving. Okay. So now we know this way of specifying them as precondition, postcondition, and as a Ho triple, right? So what do we do now? I mean, what is it that we can do? So let's look at a few more examples. So we want to, let's say, we want to find out equivalence of neural network. So we have a neural network F. We want to replace it with so let's say we have constructed a faster or a more lightweight network G, and we want to replace F by G. But before we replace, we must check that F and G are equivalent. Okay. So what is a way to specify this property that F and G are equivalent? You can specify this by writing it in this form that R1 is the result of that the network gives over X, R2 is the result that the network G gives over X, and R1 and R2 must belong to the same class or must be the same, however you define your classes. Correct? So this is to say that the two networks behave exactly the same. Okay. This property might be too strong, right? Two networks in general may not behave exactly the same, and therefore this kind of specification may be too strong. Can we work with a slightly weaker specification, which is not as strong as this? You started with nothing as your precondition was just true. So basically, there was no precondition, and you wanted the two networks to behave exactly the same, which is too strong. So let's say let's try to see if we can make it slightly weaker. Okay. So we don't want them to agree always. What if we pick a set of images and we want F and G to agree on those images, something which belongs to that set? We have picked a set of images, and as long as those two networks agree on the classification of those images in that set, then we are going to tell that yes, F and G are equivalent. Okay. Whether they are actually equivalent or not, whether it is correct to say it that way or not is not our question. We are just trying to specify certain properties. We are trying to specify stronger properties, weaker properties. We are just doing this exercise. Okay. So here is what we do. So we pick a set S. Okay, and we pick some x1 in that set. Okay, and we want to see that so suppose we have picked an image x1 in this set of images on which we want F and G to agree. But they need not agree on exactly that image. Also on if those images are made brighter or darker by some 10%, not more than that. Okay. So you construct these two new images, x2 and x3, okay, where you know that x2 and x3 do not differ from this x1 that you have picked by more than 10%. And x2 is R1 is the result of F on X2, R2 is the result of G on X3. And as long as R1 and R2 agree in the class in which they belong to, we can say that F and G are equivalent. Okay. Whether it makes sense to really say for some application, it may make sense to do that. For some other application, this might be too liberal. We're not worried about that. We are just saying that, look, here is a stronger property, and here is one way to specify a slightly weaker property. Okay. Where we don't want them to agree on everything, but agree on things which are picked from a set plus or minus some brightness. Okay. So this is how we can specify this property. Okay. Coming back to the example of this.
So the last one that you showed is already a way of tailoring your specification to suit the context. Okay, correct? So,
correct.
Yeah, so you're already doing that. You're making, formulating your specification, so variations of your specification to suit the.
Correct.
Yeah.
Okay. And it may be useful in some application. This may be wasteful in some other application, depending on the actual application. But it is still a way of specifying this, specifying a property which is weaker than the earlier property, which was very strong. Okay. So so let's take a look at this other example from natural language. So this example of sentiment classification, where the sentiment should not change by replacing when you replace a word by its synonym. Okay. Okay. So suppose you have a sentence which has n words, and I here belongs to 1 to n. I represents the word which you will eventually be replacing. Okay. How will you be replacing it? There is a sum function t, which you can think of like a thesaurus. So this will give you, for a given word ci, it will give you a word w. Okay. And then you replace in your sentence c, you replace the ith word by the new word w, which is returned by this thesaurus. Okay. So your sentence remains as it is, except that the ith word has been replaced by a synonym of it. Okay. And then R1 is the result of classifying. R1 is the result that the network gives on X. R2 is the result that the network gives on C. And you want to ensure that the class in which R1 belongs is the class in which R2 also belongs. Okay. Namely, that the sentiment does not change if you replace one word. Okay, so this is one way of specifying this property. You can specify this property, for two words also. One can consider the case when two words are being replaced. How do you specify that? So you pick two indices now. I and j both belong to this 1 to n, where I is not equal to j. Okay, so you're replacing two distinct words. Okay. How do you replace? You find out the words to be that they must be replaced by. So wi is something that the thesaurus returns for ci. Wj is the one that the thesaurus returns for cj. And then you take the sentence x, you replace the ith word by wi, jth word by wj, and here is your sentence. So this is your precondition. Okay. The network is as it is. So you compute your results. R1 is the result of computing f on x. R2 is the result that you get by computing f on c, and you want to verify that R1 and R2 belong to the same class. Okay. Okay. So all that I've been trying to explain with different examples is that you can specify these properties. We'll see how to verify these properties, but we are just trying to say that, look, not everything is lost. Neural networks may be learning all kinds of complicated functions which are doing all kinds of complicated tasks. You may not be able to specify all of it, but there's certainly some of it that you can specify, and later we will see that you can also verify. Okay. So what to specify itself is an important question, and how to specify it and so on. As I have been saying, you may not be able to specify the entire mathematical correctness, but you can still specify some desirable properties, like how we have been seeing. Okay. Yeah. So yeah, so once again, we have this, we had this example from the first lecture, right? So you have this this ownership here, which is moving, and you're trying to, you have synthesized a controller in terms of a neural network, which tells you what to do when it sees an intruder aircraft coming from some direction, by calculating the distance and the angles and the velocities and so on. Okay. So you have built a neural network which assigns a score to the actions. Okay, and what are the actions? You have these 5 actions. You either want to turn left, and these are the actions for the own ship. Okay, so you have built a neural network which is trained in this. Okay, so the neural network is trained in reading a bunch of sensor inputs, which is this theta, psi, the velocities, the distance rho. Okay, so the neural network is trained to take these as inputs, and the outputs that it has is one of these actions, which is either to turn left, to turn right, to turn sharp left, to turn sharp right, or to do nothing. Okay, and the lowest score action is performed. I'm sorry about this bracket here. Yeah, so the lowest score action is performed. Okay, so this is how the network behaves. Okay, now one of the property that you may be interested in is that if an intruder aircraft is far, and if it is approaching at a low velocity as compared to own velocity, then it is okay to not panic. In other words, it's okay to do nothing. Okay, how do you specify this? You specify this. Okay, and when you have to specify this, you need to understand what is meant by far. We are talking about aircraft, so maybe a few kilometers is not far. Okay, we are talking about velocity, so we have to understand what is a high velocity, what is a low velocity. So it requires domain knowledge, like how we had this question that if the code is equivalent, is it always true that if one is detected as malware, the other should always be detected as malware? This is something that comes only from the domain knowledge. Similarly here, it comes only from the domain knowledge, what is meant by far. So here perhaps 55,000 feet or kilometer could be considered as far. So your rho has to be bigger than 55,000 feet. Your own velocity is bigger than this. Your intruder velocity is less than equal to 60. So this may be your precondition. Okay, and then your post condition is that the score of nothing has to be below some threshold. You don't want to panic, so you agree that with there is a high chance that you don't want to do anything. Okay, so this is your post condition, and one can put the network in between. So you have your pre, you have your post, you put your network, you have your whole triple, and you can convert it into the validity problem, and then write it as an unsatisfiability problem, and give a satisfiability solver to check whether there is a satisfying solution or not. Okay. Yeah, so the point that I wanted to stress here is that it's difficult to specify, and it needs domain experts sometimes, because you don't know what is a desirable property, and what what is a precondition, and what is a post condition, and so on. Okay, so this is all that I have for today. I will get back to yeah. So if there are any questions in this part, I will take that. Otherwise, I'll get back to the question that was raised earlier. Yeah. Does anybody have any questions?
I have another comment / question about something else, but that's probably less relevant. So if anyone else wants to ask, they can go first.
Oh no, I wanted to ask about this equivalence of neural networks.
Correct.
So yeah, I saw. So in the side we saw how we can logically code it, but the current deep learning community or researchers, how do they check the equivalence of a lightweight neural network, whether it can replace a heavy neural network? How do they do it currently?
Correct. So I don't know how they do it currently, but I strongly believe that this is how they do it. You specify what it means to for two things to be equivalent. Correct, because one way in which you can do it is by dumping the network and by checking that look, it is element wise the same. Correct.
Yeah.
Okay, the weights are the same, the biases are the same, it's all the same, it's exactly the same thing, right? If it is not the same thing, then then there is no question of checking it, checking element wise that it's the same thing. You just cannot, right? So the only way that you can check then is to check certain properties, okay? And one way is to check that, on some difficult examples or some carefully chosen examples, those two behave the same.
Yeah.
Yeah, but your question, may I know who was that? Who asked that question?
Sir, me, Pratik.
Pratik. Yeah. Yeah. So I guess, yeah. Structurally, if they are different, you can ask a question about if they're structurally somehow equivalent, or after defining what structurally, so the syntactic structures, maybe if they are equivalent, then there may be sufficient conditions to make the outcome the same for all things. But more likely, specifying structural constraints and conditions might be very difficult, I think, I would imagine, because these networks are so huge and there could be small, differences. I'm not sure how exactly, a practitioner would get it. I would imagine that if you want to have two different networks, you will have to use these kinds of properties, okay? Define what are the properties that that you care about, okay? And with respect to those properties, whether they behave the same way, that is what, for all practical purposes, regardless of how different the internals are, that's what you care about, isn't it? So
Yeah. So this is yeah. So this is this is the only way to do it. I mean, yeah, internally, and I mean whatever, in this, what are the properties, whether somebody specifies a big set, somebody specifies a smaller set, whether somebody wants to give this leeway of this 10% change or not is a different thing. But eventually, this is what you can do. How do you know that they are the same? You verify. You state this as a property and you try to prove that property. So typically, this is not traditionally, neural networks or they are considered as opaque objects, and people have, at least, not for very long, people have not been looking deeper into them and trying to find out or argue whether they will do what they are supposed to do or not, or are they equivalent or are they not.
yeah, this would also be, I don't know, since Siddharth knows a little bit more about actual designs and so on, I wonder if this would be useful. So, for example, if you keep adding more internal nodes, will it really matter? Okay, for example. That could be a question that kind of mixes both structure, which is lightweight as opposed to heavyweight. So if I keep adding more nodes, internal nodes for certain hidden layers, maybe will it improve or it may not, okay? So whether those kinds of questions are relevant, okay? So do you have any comment, Hitat, in terms of, are there, such proving properties relative to, all the properties that Madhuka showed were perturbations to the inputs, okay? Which is the most relevant thing. And most of the work that I have come across in applying SMT logic and verification techniques do prove such robust properties. So the question that I'm asking is, if perturbations to the structure of the network in terms of nodes or connections and so on, how that will impact the behavior, if that is relevant. That's the question that I'm raising.
Yeah, so I don't think Hitat is there today.
I see. Okay. Yeah, no, I don't know. That's something, that question we could find out.
Correct. Yeah, we can find out, but but also, remember that this is a fairly new field where, people are trying to argue about neural networks. It's not more than a few years old.
That is true. That is true as far as application of SMT solving and program verification techniques are concerned. But what I'm saying is, if a practitioner is doing that, such asking these questions and using traditional simulation and methods, then maybe that relevance is there. And if we can find out, or you can find out.
Certainly.
Then you means the class, I'm saying. Okay.
Correct. No, yeah, and including me.
Then we could formulate those things as SMT problems and investigate. Okay, so
yeah.
Yes, Sahil. Yeah, anybody else? Yeah, Sahil.
I'm sorry, I missed that. Did you ask me a question?
No. I thought you had a question or a comment. That's what.
Oh, okay. So Madhukar was about to explain his example, I think, first.
Yeah. So I think, so I can construct a small example, and which is what I'll try to do here. Let me. In fact, there's this. Wait, Yes, so I can perhaps open something, but I'll try to give you I'll try to give you an intuition. So suppose you're trying to you have to insert an element into an array. Okay. So you have to insert an element into an array, some element at some. So suppose the given array is sorted, and you are trying to insert an element at its appropriate position so that the array still remains sorted. Okay. So you are trying to do that now. So there are two programs which do that, right? So one is that you find so you take a iterator, so you take a variable I, and then you start from the first thing. You compare whether the value that you have is bigger than the current value, and then so on. You move it till you find an appropriate place and you insert it. Okay. So suppose you have two programs. One program inserts it, and then simply returns. The other program inserts it and then takes the iterator all the way to the end, even though it is not really needed for the insertion, right? So suppose you have inserted it and then you left the iterator as it is. The second program takes the iterator and pushes it all the way to the end, so that the fact that where you inserted it can be hidden. Okay, that does not come out by the value of the the iterator. Correct. Now, these two programs are the same, but remember that, if
they're not exactly the same, but they are equivalent with respect to the specification of insertion. Okay. Yeah. Actually, from an outside world, they're exactly, they are, I guess Sahil would argue that they are not exactly identical. Okay.
Correct. So then,
as far as your spec of insertion is concerned, they are equivalent.
Correct. So first of all, is the example clear, Sahil?
Yeah, I'm sorry. Some of the doors I missed some part, but it's basically clear. Yeah.
Correct. So you're trying to insert a value into a sorted array, but somehow you want to not give away the index at which you have inserted. So you can write two programs, one where you leave the index as it is. In the other one, you anyway iterate through the rest of the array, even though you have found a place, but you anyway iterate through the rest of the array. So so as Sir was saying, it's not, one can argue whether these two programs are equivalent or not. But
let's assume they're equivalent with respect to the specification.
Correct. Yeah, in terms of any visible action that they are doing, they are equivalent. Okay. But, one still leaves it open for, an intruder to find out where you might have inserted the new value. Okay. And the other one does not.
Yeah.
Now,
Repeated experimentation, you will be able to infer more thing about how the algorithm works, in the first one. Okay. Therefore, in that you can exploit to do some mischievous things.
correct. Yeah. So one can still argue that, look, they are not equivalent, but I'm saying that, now we are already, talking we are talking very specific things about a domain, which is, and then it becomes an application specific thing or a domain specific thing, whether this is equivalent or not equivalent. It becomes it becomes a question about that particular application or that domain. So it needs to be specified mathematically, and then we can verify these properties.
Right. So in case of malware, you'd probably want to err on the side of false positive rather than false negative. And so
Correct.
I guess this again, the conjunction is what is throwing me off. If it was a disjunction, equivalent or syntactically similar,
Correct.
that would make sense. That still would seem to make more sense to me. But yeah, I have to think about this.
Correct. Yeah. Perhaps. I do see the discomfort, but that is that's slightly orthogonal to the subject anyway. I mean, whether it's a conjunction or a disjunction, the idea is to specify a property and to check it, and whatever property you think is appropriate. I mean, somebody may argue that 55,000 feet is perhaps not safe enough distance. Somebody may argue that 55,000 feet is indeed a safe enough distance to not worry about an intruder aircraft. So
Right.
what I'm trying to
Yeah,
say
you're
when
right.
it gets into the details of the domain, it's the fact that you can specify the property and verify it is still relevant to in some sense. Yeah.
Right. So the other question / comment I had was around your replacement of the softmax with x by
Correct.
x plus y and y by x plus y. So this is not something I've seen before. Usually people do go with softmax. And I was thinking about it. And so for example, if the output is, so it won't matter if you're only interested in the one with the maximum value, but
Correct.
usually softmax is interpreted as a probability.
Correct.
So that holds for your case if x and y are positive, and except for edge cases, it seems to work fine.
Correct.
But the softmax has I think has a lot of fundamental motivations. And so, for example, one property that yours won't satisfy. So if you have an output, one of the output neurons is 1, and the other, suppose we're classifying two things like cats and dogs. And one output is 1 and the other output is 2. Then the probabilities you'll get is 1 by 3 and 2 by 3. And it could easily be the case that instead one of the outputs is 20 and the other output is 21. And then the probability really changes a lot.
Correct.
Whereas in softmax, this is not a problem.
Correct. No, I totally agree. And I'm not trying to say that, look, it's a replacement. I just meant that, for the purpose of verification, since, the exponentials are, it's difficult for an SMT solver to digest. We can at least, for a 2-class thing, for our purpose, for this example, we can do this and we can check these properties. Yeah, I totally agree. Yeah. Softmax is, I'm not trying to, I was not trying to suggest that you can replace softmax.
Right. And anyway, it wouldn't matter if you're just interested in the best classification. I'm only bringing this up in the form of like, if you're trying to interpret all of the outputs as probabilities, so
correct,
it wouldn't matter anymore.
Correct. In fact, there is a nice discussion, and I failed to include it in there's a link which I'll share. When I upload these slides, I'll upload them with the link. There is a nice discussion on why softmax indeed works so well. And I think it will be good for people to look at it. I mean, you might be aware of it, but some others may take a look at it. Yeah. So indeed, what you say is very correct. Softmax has a lot of nice property, and it is we should use softmax when we are doing this classification. It's just that the verification becomes difficult, and in this course we might be making certain assumptions or certain simplifications for the verification to succeed. later we can certainly come back and ask this question that, how do we still make verification succeed with these non-linear things? Can we approximate these non-linear things and, and at least, so when we are asking this question of verification, we are asking both the proof as well as a counterexample, right? So now if I'm able to, if I'm willing to get rid of the proof or get rid of the counterexample, basically, soundness or completeness, if you think about it. So if I'm willing to get rid of one, can I still ask some questions by approximating these functions instead of overly simplifying them? Can I approximate it and do better? So we'll try to see some of this in the next few lectures. Any other?
Yeah. So what Pratik asked about replacing heavyweight with a lightweight. So I missed some of that discussion, but so we would, if we have a higher or as good of an accuracy,
Correct.
then we wouldn't really care about equivalence, right?
Correct, but it will only be on the training data, right?
No, so the example that Pratik gave was, for example, if you have I don't know, 10 million parameters, and we've discovered that, oh, we can get away with like 10,000. And then we're like, okay, the 10 million parameters one got 97% accuracy, and the 10,000 one gets 96%, and that's good enough. We don't really care if there's an equivalence across any particular class of examples or anything like that, right?
Correct. No, but how do you know that? So say when you computed these accuracy figures, you must have used some data.
Yeah, right.
Correct. What if there is data outside that thing?
Yeah, but so that's like a general problem, right? So generalization error is something that's always a concern.
Correct. So when we ask these questions about verification, when we are trying to verify that, look, then we somehow address that problem also, right? I mean, we may be able to verify for weaker properties. That's true. But in general, when we are solving this question of verification, we are saying that, look, it's never going to be the case. No matter what training data you bring, these guys will
right. So I'm talking specifically about the equivalence part rather than just general verification. So it seems to me that would be less relevant to industry use or just in practice.
What would be less relevant, Sahil? So equivalence would be less relevant?
Yeah, so equivalence of neural networks is sort of not relevant as in my mind, as long as accuracy is as good or higher of any network. And of course, accuracy is sort of dependent on what sort of test data you use, like Madhukar's pointed out. But yeah, that's probably just good enough. We wouldn't actually want to worry about equivalence.
Correct, but this is also because traditionally these are they are not used in I mean now if you think about it, if these if neural networks are being used for safety critical applications, then then the hope is to be, I mean, at least the aim is to be more careful about these predictions, right? Instead of empirically testing. I mean, there's always this question of testing versus verification. So.
Right, yeah. So one thing that we used to do, so you gave the synonym example, right? So when I was working and we had like language models, what we would do is actually like generate more data, take the existing data and like generate more data with synonyms replaced with that synonym replacement. And of course, that's like a soft way of doing the similar specification. So I guess like you could just use a standard model to maybe not as rigorously enforce things, but probably still get much of the way there. Like you could take an image data set and add all of the images with one pixel changed. Of course, that's a huge number, but yeah, that is something I think people do in practice anyway.
Yeah, certainly. Yeah, so practically, yeah, certainly, there are ways in which we can answer. We are just trying to say that, look, there are ways in which you can answer some of these questions rigorously also, because of all the tool set that verification makes available. That's the point that we are trying to make. Yeah.
Okay. We are approaching 5. Okay. So
yeah,
I have just like one.
Yeah, one more question. So I guess if people don't want to stick around, that's okay. So discussion.
Hello?
Go ahead. If there was some other question.
Yeah, certainly. Go ahead.
So, so I had just like one small questions about when we're like say picking a class of examples on which we want to like when we're weakening the verification condition by picking a class of examples, or say when we are trying to verify the neural networks by like the sentiment predictor by say switching a word with its synonym, we do not have any good like symbolic representation of what we mean by a synonym, or may not have a good symbolic representation of a example class, right? So
Correct,
in
correct,
that
correct.
case, the verification, like the things we need to verify, just will be a large set.
Correct, correct. True, 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 true. Yeah, yeah, correct. Which is very true. So I simply, assumed a function called T, which given, a word returns a synonym of it, right? So I use that function T in our example. And, to specify this T is a difficult task, right?
Right.
Because, this T is like, an entire thesaurus. So basically, it's a difficult task. That is true. It is difficult. So it may be difficult to specify this property and difficult to verify this property. What we saw is that it is, I mean, whatever, given that this can be specified, here is how you would write your correctness property as.
It's in some sense theoretically possible.
Correct, 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 correct. I
This
mean, if you write a small
specification
enough,
is
thesaurus for some 10, 20 words with, some 3 synonyms for each word, maybe there is a way to represent it mathematically, and, you can still do it, right? So in principle, you can do it. Of course, the general problem continues to remain difficult to verify because specifying is a difficult task in this case.
Yeah, but no, it's the reverse, isn't it, Madhukar? Because if you, I mean, the specification is easy in the sense you have, this synonym as a set, okay? So as a set of words. So one is replaced by the other, replacement can be defined as a function, okay? Which takes an element of that set and then returns some other element of the same set. It is the verification that has to almost enumerate across the entire set, isn't it? So, how else will you know whether it is doing it correctly? See, if it's some real input, etc., then I can understand. I mean, you can use properties of real arithmetic and so on. So, whereas if these words are synonyms, I mean, unless you can capture what it means to be a synonym in some other way as a word property or something, which is difficult. Yeah. So in that sense, the spec is difficult too. But certainly, if you just
so the verification, yeah. So I agree that the verification, it comes down to enumeration, but but still it is enumeration over some finite set.
yeah, but it's a large, yeah.
Correct. So yeah, I mean I agree. So in that sense, it is certainly a difficult verification problem. But verification anyway is assumed to be as difficult as enumeration in the worst case for a finite set. So
Sir, I have,
I think that, it's not that the verification which gets more difficult; it's the specification which gets more difficult. In that sense, I was saying.
sir, I have a question about verification.
Yeah.
These days you have these sophisticated neural networks like UNets, which are used for these biomedical image segmentation. So they are only used for medical sciences.
Okay.
So when we talk about verification of such neural networks, it is very important that they get those critical edge cases right, right?
Correct.
Someone can lose their life because this neural network was not able to catch some
Correct.
segment of the image with cancer or with diseases.
Correct.
So even even starting to verify, or you know getting those getting to know which critical edge cases it fails on, it is difficult in its own right, right?
Correct. Correct. It is
Yeah.
difficult in its own right. Correct.
Yeah, because the verification is the next step. First step is to make sure that this neural network gets this thing right.
Yeah, but see, but then for this example, if you're able to, I mean, even if you don't know what the corner cases are, but if you know that if you specify, oh, for all inputs, for all values, it should never, the tolerance should never be too wide, okay? If you can do it, then if there are cases, corner cases for which that property does not satisfy, this verification can show you that. Hey, look, for these corner cases, it is violating that. Correct? So maybe
Yeah.
you'll be able to make.
So for instance, suppose you're trying to learn whether to administer a medicine or not by looking at some images of the patient or some some issue there. So yeah, so you can try to ask this question that will it ever be the case that the network will give a certain dose even though the problem was not exactly there or some such thing, right?
Yeah, exactly that.
And you can, and so if you're able to specify this property, the verification engine allows you to construct a borderline case for which it will be the neural network will treat it wrongly. So it can construct this as a counter example. It can construct that example for you which will be classified wrongly.
Okay. Yeah.
Of course, the specification remains a challenge, and the verification capabilities as of now it remains a challenge, because we are struggling with nonlinear. Maybe we'll be able to push the boundaries a little more in the next few years, and a little more in the next few years. So eventually, these things may become easier and easier, and but the specification for any given application is a challenge, and that problem has to be solved first before we come to verification.
Thank you, sir.
Okay. Good. Good discussion. So, any more questions? If not, shall we adjourn?